Hello, everyone. Again, thank you for your patience. We are super excited to be here and talking to you about TensorFlow.js and how to bring machine learning to JavaScript applications. My name is Brijesh. I'm a technical program manager on the Google TensorFlow team. And here's my colleague, Kangyi, who's a software engineer on the TensorFlow team. So here is an outline of what we are going to cover in this talk. We will start with the what and why of TensorFlow.js. We will see some of the ready-to-use models that TF.js supports. We will do a code walkthrough of the development workflow, both to use one of these pre-trained models as well as training a custom model. We will delve a little deeper into the tech stack and the roadmap. We will show you what the community is building with TensorFlow.js. There are some very impactful applications that are being built, and we'd love to show you some examples. And finally, we'll point to some resources that you can start exploring. All right, so we have a lot of exciting content to cover, so let's get started. You may have heard at the TensorFlow.js keynote an overview of the technology today morning. We are going to build on that here. But first, a quick recap of the basics of TensorFlow.js. So in a nutshell, TensorFlow.js is a library for machine learning in JavaScript. It is built for JavaScript developers to create and run machine learning models with an intuitive JavaScript-friendly API. This means you can use it to perform training and inference in the browser, browser-based platforms, and in Node.js. ML operations are GPU accelerated, and the library is fully open source, and anyone is welcome to contribute. Okay, so TensorFlow.js provides multiple starting points for your needs, right? So you can use the library. You can directly use off-the-shelf models that the library provides, and we will see a lot of these in a bit. You can also use your existing Python TensorFlow models with or without conversion, depending on the platform that you're running on. Or you can retrain an existing model with transfer learning and then customize it to your data sets. That's the second starting point. Transfer learning typically needs a smaller data set for retraining, so that might fit your needs better. And the third starting point is you can build your model entirely from scratch with a Keras-like layers API and train it. You can train it either in the browser or on server with Node.js. So we are going to delve much deeper into some of these workflows today. JavaScript, of course, is a ubiquitous language. So by virtue of that, TensorFlow.js works on a variety of platforms. It lets you write ML code once and run it on multiple surfaces. As you can see, the library runs on any standard browser, so regular web apps, progressive web apps are covered. On mobile, TF.js is integrated with mini app platforms like Wechat. We have just added first-class support for the React Native framework, so apps can seamlessly integrate with TensorFlow.js. On server, TF.js runs on Node. In addition, it can run on desktop applications using the Electron framework. All right, so why TensorFlow.js? Why run ML in the browser? Right, so we believe there are compelling reasons to run ML on a browser client, especially for model inferencing. Let's look at some of these reasons. Firstly, there are no drivers and nothing to install. You include the TensorFlow.js library, either at page load time by script sourcing it into your HTML page, or by bundling with a package manager into your client app, and you're good to go. That's it. The second advantage is you can utilize a variety of device inputs and sensors using standard device API, such as camera, microphone, GPS, through standard web API, HTML API, and through a simplified set of TF data API. And we are going to see some examples today. TF.js lets you process data entirely on the client, which means it's a great choice for privacy-sensitive applications. It avoids round-trip latency to the server. It is also WebGL accelerated. So these factors in combination, combine to make for a more fluid and interactive user experience. Also, running ML on the client helps reduce server-side costs and simplify your serving infrastructure. For example, no online ML serving that needs to scale to increasing traffic and so forth is needed because you're offloading all your compute to the client. You just host a ML model from a static file location, and that's it. On the server, there are also benefits to integrating TensorFlow.js into your Node.js environment. Right? If you are using a Node.js serving stack, it lets you bring ML into the stack as opposed to calling out to a Python-based stack. So it lets you unify your serving stack, all in Node.js if you're using Node.js. You can also use your existing core TensorFlow models to bring them into Node.js, not just the pre-built off-the-shelf models, but rather your custom models that were built with Python TensorFlow can be converted, and in an upcoming release, you don't even need the conversion process. You can just use them directly in Node. And finally, you can do all of this without sacrificing performance. You get CPU and GPU acceleration with the underlying TensorFlow C library because that's what Node uses. And we are also working on GPU acceleration via OpenGL. So that removes the need for depending on CUDA drivers as well. So effectively, you get performance that's similar to the Python library. So these attributes of the library enable a variety of use cases across the client-server spectrum. So let's take a look at some of those. So on the client side, it enables you to build features that need high interactivity, like augmented reality applications, gesture-based interaction, speech recognition, accessibility, and so forth. Right? On the server side of the spectrum, it lets you have your more traditional ML pipelines that solve enterprise-like use cases. And in the middle, that can live either on the server or on the client, are applications that do sentiment analysis, toxicity and abuse detection, conversational AI, ML-assisted content authoring, and so forth. So you get the flexibility of choosing where you want your ML to run, on the client, on the server, either or. So whatever your use case is, TensorFlow.js is production ready to be leveraged. So with that intro, I'd like to delve deeper into the ready-to-use models available in TensorFlow.js. Our collection of models have grown and is growing to address the use cases that we just mentioned, namely image classification for classifying whole images, detecting and segmenting objects and object boundaries, detecting the human body and estimating pose, recognizing speech commands and common words from audio data, and text models for text classification, toxicity, sentiment detection. You can explore all of these models today on GitHub. You can use them by installing them with npm or by directly including them from our hosted scripts. So let's dive into a few of these models and see more details on these. So this is the PostNet model. It performs pose estimation by detecting 17 landmark points on the human body. It supports both single person and multi-person detection within an image. Now, there are multiple versions of this model, versions that are backed by MobileNet and those backed by ResNet, that provide options for balancing accuracy versus model size versus latency, depending on your needs. And it enables use cases like gesture-based interaction, augmented reality, animation, and so on, things that are well served by running ML on the client. By the way, you can explore a demo of this particular model at our booth in the expo hall. Another human model is the BodyPix model. BodyPix enables person segmentation, again, both single and multiple persons in an image. It identifies 24 body parts, such as left arm, right arm, torso, left, right legs, and so forth. It also provides convenience API to segment and mask each body part in a different color, which is what you're seeing in this particular GIF. And in terms of use cases, you can be used for things like blurring faces in an image or blur the background. say to protect privacy. The Coco SSD object detection model enables object detection of multiple objects in an image. It detects about 90 classes defined in the Coco dataset. And the nice thing is it takes as input any browser-based image element, like an image or a video or a canvas element, and returns an array of bounding boxes with the detected class and a confidence level. In this sample image, you can see that the kite is detected with a high confidence score, and you get a bounding box. There is also a deep lab model which offers semantic segmentation that's coming soon, yet to be released. So what I'd like to show you here is how easy it is to use a model like that, like Coco SSD, in your JavaScript app without dealing with tensors, transformations, or layers. And this pattern really applies to any of our pre-built models. Right, so first, you script source the library in your HTML file from the hosted CDN. Alternatively, you can just npm install the library and use a build tool like Webpack to bundle into a client.js file. Then you load the model. That's the .load method. And you call the model.detect method on the image element that you are trying to analyze. And that's it. What you get back is an array of objects that have the bounding boxes and the classes that are detected. So really, 4 or 5 lines of code to end up leveraging a powerful ML model in the browser. Text models are another useful set. TF.js has a toxicity detection model and a more general universal sentence encoder model. So let's look at the toxicity model a little closer. I want to show you a live example of this model in a web app. Give me a second. Okay, there you go. So here is a super simple web app that simply loads the model and passes a few sentences to it. And what the model does is classify it on a few dimensions, like does this signify an insult, is there a toxicity, is there a threat, and so forth. So let's try an example here. So I'm going to say something toxic. If I can see it, ignorance is ready. Okay, so something that I would think is toxic. So that returns as toxic as well as returns as an insult. However, this model, I want to show you that this is context-based, not keyword-based. So you type the same word in a totally non-toxic context. You're going to see a different answer, and that's detected as not an insult. So this sort of model can be used on the client side in product reviews or in chat type of situations. Here is an example I want to show you from a Twilio developer who integrated TensorFlow.js into a chat app. And again, here it's able to detect that comments, toxic comments, and filter them right before sending. All right, so next slide. Another interesting model is face mesh. This model provides high resolution tracking of facial features. So it detects about 400 points on a person's face. So we believe that this model has great potential for real world applications. For example, detecting facial gestures, emotion, supporting richer accessibility features, and so forth. So now I'd like to show you a couple of cool demos built using face mesh. First up, and you might have seen this in the keynote session today morning if you attended. Here's an application built by one of our partner teams at Google. This app is called LipSync. This is a game that tracks how well you are lip syncing to a song, all real time in the browser. Right, so let's see a demo. Notice in particular how the display turns gray when the lip sync doesn't match the lyrics, and how the score kind of matches how well the person is lip syncing. So when the lip syncing when the person is not lip syncing correctly, then there's feedback given back to the user, and this you can see is a type of example that one can build entirely on the client using this library, and sort of let your imagination go from there. So again, this is available at the TensorFlow.js booth. You're welcome to try and see how you do. The next application we'd like to highlight is a virtual makeup try-on app, again using face mesh. So this is a mini app that the company Modiface, which is a subsidiary of L'Oreal, has built on the popular Wechat platform. I would like to invite Brendan Duke from Modiface to come on stage and show you how they use TensorFlow.js to build this app.
Thank you. Thanks, Brijesh. So hi, I'm Brendan. I'm a research scientist at Modiface. And first, let me briefly introduce Modiface. So Modiface is an augmented reality for beauty company. It was founded in 2007 in Toronto, Canada, and acquired just last year 100% by L'Oreal. So today, Modiface collaborates with 20 beauty brand subsidiaries of L'Oreal, such as L'Oreal Paris, Maybelline. And you can find our technology in such online retail giants as Macy's, Sephora, or Amazon. So now I'm going to talk to you about how we make use of TensorFlow.js in our virtual try-on applications. So in order to introduce why we need a framework like TensorFlow.js, I'm going to use the Wechat mini program, for a makeup virtual try-on that we developed as an example to showcase the kind of challenges that you run into when you're deploying real-time virtual try-on systems. So first of all, we want to deploy our applications on the client side. This is for user privacy and to avoid the latency from doing a round trip to a backend server every frame. And also, we have a soft requirement of about at least 10 frame per second frame rate in order for our applications to feel interactive. So this is particularly difficult on the Wechat platform because you have to run your mini program in Wechat's JavaScript environment, and you inherit the limitations of JavaScript. So we needed both to develop a lightweight Spartan model for our face tracking, and also to find a framework that runs quickly in JavaScript, and ideally makes use of WebGL to run deep learning operators using the GPU hardware acceleration. So a second challenge we ran into is that the Wechat mini programs have a 2 megabyte cumulative file size. So we need to find a framework that's small and allows us to develop a small model, and so that we can load it as quickly as possible as well. And thirdly, because our models have some custom operators, we needed a framework that's extensible with custom operators. And we also needed a framework that is going to support all the different mobile phone models that are supported by Wechat itself. So now I'm going to tell you about how TensorFlow.js fit the bill and was able to overcome some of these challenges that we ran into in deploying our makeup virtual try-on. So first of all, TensorFlow.js runs on the client side, and because it makes use of WebGL backend, it's able to harness the mobile phone GPU hardware acceleration, and which gives it like a an order of magnitude speed up over browser-based CPU solutions such as WebAssembly, which are kind of limited right now by lack of SIMD and multi-threading. So TensorFlow.js really allowed us to hit our frame rate requirement. And second of all, the TensorFlow.js library is small and compact. We were able to package the library in about 700 kilobytes. And combined with our roughly 400 kilobyte model sizes, we were able to fit everything within the Wechat mini program file size limit. And thirdly, TensorFlow.js both has widespread support for built-in deep learning operators and also allowed us to extend it with our custom operators that we need for our face tracking. And finally, TensorFlow.js is supporting a wide variety of mobile phone models and has continuous support from the TensorFlow.js team. So for these 4 reasons, we chose TensorFlow.js as the framework to deploy our makeup virtual try-on on the Wechat plugin. So now I'd like to share with you some of our results. So with the help of TensorFlow.js, we were able to successfully deploy to Wechat our easy-to-use real-time system for realistic AR virtual try-on of makeup. Our entire final solution fit into about 1.8 megabytes. It's including the code and our models. And on an iPhone XS, our rendering and tracking together run at over 25 frames per second. So TensorFlow.js coupled with our tiny CNN face tracking model allowed us to deploy to web our fastest, smallest makeup virtual try-on system to date. So now I'd like to briefly mention a few future research directions that we have going on at Modiface. So we've already used TensorFlow.js to create web application demos for our makeup try-on, our hair color try-on, and our nail polish try-on. And in particular for our hair color try-on, we were able to achieve an order of magnitude speed up on a guided filter operator that we use as a post-processing step by just taking our WebAssembly implementation of that operator and re-implementing it in TensorFlow.js. This amounted to about a 20 millisecond reduction in latency for the whole system. We also have a number of other research projects going on at Modiface, such as hairstyle transfer, virtual aging simulation, and skin analysis that we hope to use TensorFlow.js to deploy in the near future. So thank you everyone for listening, and I'll pass the presentation on to Kangyi.
Thank you, Brandon. Hi, my name is Kangyi. I'm a software engineer on the TensorFlow.js team. Next, I want to walk you through the workflow of developing apps with TensorFlow.js. We just saw the Modiface Lipsticks virtual try-on app, and I want to show you the details of building a sunglasses virtual try-on app, which uses augmented reality to allow users to try sunglasses through the camera in a web page. To build a sunglasses virtual try-on app, there are several components. First, we need a model that is trained to find the face. And second, the model needs to be loaded in the app to run inference. And third, the app needs to get video data from the camera. And some pre-processing is required so the video data is compatible with the model as input. And after the model inference, we need some post-processing to use the model output data. And finally, the sunglasses need to be rendered based on the model output. The first technical challenge is to get input data from the camera. TensorFlow.js provides a data API which enables developers to easily get data from a web camera, microphone, image, text, and CSV file. This data API will also prepare the data as tensor, so it's ready for the model with customized configurations. And the second technical challenge is to detect the face in the camera and find key points on the face. Previously, we have seen the face mesh model, which is pre-trained to identify up to 400 facial key points in 3D coordinates, and it is a great model for this task. The third key challenge is to post-process the model output and display the sunglasses. After we get the key points on the face, we want to render the sunglasses on the right place. And we find 3.js, which is an open source cross-browser library used to create and display animated 3D graphics in a web page through WebGL. It will be used to render the sunglasses onto user's face. And let's walk through the workflow diagram again. We take the video frame from web camera through TensorFlow.js data API and transform it into tensor that can be consumed by the model. We run face mesh model in the TensorFlow.js runtime to detect the facial key points, and then use the model output to put the sunglasses graphics on the right place. And finally, we use 3.js to render the sunglasses in the browser. And now let's start coding it. In the HTML file, we started by loading the TensorFlow.js library and the face mesh model from our hosted scripts. And next, we add a video element to hold the web camera as input and another container to hold the rendered output. And here's how we will use the model. First, we load the model weights asynchronously, and then use the TensorFlow.js data API to get image frames from web camera, and then use the model to do an inference. The inference output is a JSON object containing the facial key points in 3D coordinates. And here we prepare the sunglasses image to be rendered in live web camera video. To display with 3.js, we need to have a scene containing the sunglasses image, a camera containing the video, and a WebGL renderer so that we can render the scene within the camera and display it. And finally, we create a loop through a request animation frame, and in each loop, we get an image from the camera, predict facial key points in the frame, and render the sunglasses onto the video. And let's see how the app finally looks like. Okay, so let me first add the face mesh render result. I'll just refresh the page and reload the model. And it takes several seconds to load the model. And okay, so you can see it shows the detected key points on my face and also the sunglasses. Okay, and this demo is built with a pre-trained model we provide. And we also support using pre-trained Python models in JavaScript. We provide a command line tool to bring TensorFlow saved model, TF hub model, and Keras model into JavaScript. It supports more than 200 ops, and also it supports both TensorFlow 1.x and 2.0. To use a Python model, first use the command line conversion tool we provide to convert the model into JavaScript-friendly format. And then the converted model can be loaded through TensorFlow.js API in JavaScript applications. And then finally, you can use the model in the same way as the model we provide. And what about other problems that there is no model available? We provide a layers API, which is a Keras-compatible API for building models, and the lower-level op-driven call API if you need fine control of model architecture or execution. And let's see how to build and train a model from scratch with TensorFlow.js. First step is to import the model. And if you are working in Node.js, you can also use the tfjs-node library, which executes the TensorFlow operations using native compiled C++ code. And if you are on a system that supports CUDA, you can also import tfjs-node-GPU library to get GPU acceleration when doing training or inference. And this is what creating a convolutional model for an image classification task looks like. As you can see, it is very similar to Keras code in Python. We started by initiating a sequential model where the outputs of one layer are the inputs out to the next layer. And then adding a 2D convolutional layer and a max pooling operation with configurations. And then finish the model definition by adding a flatten operation and dense layer with the number of output classes. And once the model is defined, we compile the model and get it ready for training. Here we select a loss function and an optimizer for the training process. And model.fit is the function that drives the training loop. It is an async function, so we want to wait for the result. Once the model is done training, we can save the model. Here we save it to the browser local storage. We also support saving to a number of different destinations, such as local file system or remote URL. And finally, we can use model.predict to get a result from the trained model. And next, I want to show you the tech stack and upcoming features in TensorFlow.js. We provide 3 layers of APIs. The top layer is the pre-trained models ready to use out of the box. In the middle, we provide layers API to easily build and train model. And in the lower layer, we provide an op-driven call API, so users can do fine control of model architecture or for linear algebra calculation. On client side, including on browser and on mobile platforms running hybrid JavaScript applications, our library is using WebGL for acceleration. It detects the WebGL version and automatically uses it. And on server side in Node.js, we use TensorFlow CPU and GPU C library under the hood. Soon, we will release support for headless GL backend as well, which will provide GPU acceleration without dependency on CUDA. And this is the core architecture of TensorFlow.js. We have multiple acceleration options for machine learning operations faster on both client and server side. You can bring Python Keras model and load it with layers API, or use TensorFlow saved model and execute it with core API. And this is the performance benchmark on client side. On laptop and iPhone, the mobile net inference time you can see is comparable to TensorFlow Lite, and we are working hard to improve the performance on Android. On server side in Node.js, which is using the TensorFlow C library, you can see the mobile net inference time is also comparable to TensorFlow Python. We just had an alpha release for React Native support. You can use TensorFlow.js directly inside the React Native app with WebGL acceleration and load models in the same way as browser. And this is a React Native demo app performing style transfer on an image. First, it's taking an image of the picture and then take the style image. And this is the final result. And we are very excited to announce that Google Cloud AutoML now supports TensorFlow.js. You can train customer models using AutoML Vision Edge for both image classification and object detection. All you need to do is to upload the images and labels in the AutoML page. And then AutoML takes care of creating the best model for your training data and provide evaluation details. You can also choose whether you want higher accuracy or fast prediction or best trade-off. And after training is done, you can export a TensorFlow.js compatible model and use it in your JavaScript application. No model building or training code is necessary, and you can get a model through clicking in the Google Cloud platform. And this is the sample code of using a model from Google Cloud AutoML. We provide APIs to load the AutoML model, and you can use it in the same way as all the other models in TensorFlow.js. As we mentioned in our keynotes, the beta users have already seen impressive performance improvements. And in the future, we will bring more pre-trained models based on real-world use case, such as auto-reply and conversation understanding. We are also bringing usability improvements for server-side inference. Soon, we will support native saved model execution without conversion. And we are developing new backends with WASM and WebGPU to improve the performance in browser. And React Native will have a full release soon. And the TensorFlow.js community is building awesome and inspiring applications using machine learning in browser. We would like to highlight one such example from Mila. Mila researchers have built a radiology assistant tool to analyze chest rays and make disease predictions, all inside the browser app. To tell us more about this tool and how they use TensorFlow.js, I would like to invite Dr. Joseph Paul Cohen from Mila to come up on stage.
Thanks. Great. So, okay. If we take a look at the traditional diagnostic pipeline, there's a certain area where physicians are already using web-based tools to make and help them make diagnostic decisions about a patient's future. For kidney donor risk or cardiovascular risk, these are already online as early as 2006. So with advances in deep learning, making diagnostic predictions from chest x-rays using deep learning, the next step is to also put that online in a way that's usable by these doctors. And you can imagine such use cases for this in emergency rooms where humans are time limited, so we want to have them make less mistakes, right? Especially if they're focusing on something and they don't focus on something else that may be important but not their immediate concern. You can also have rural hospitals, right, all over the world that can access things through the web, right? Maybe there's no radiologist nearby to help them make that decision, right? And maybe the country doesn't even have remote resources to aid in them making that decision. So using these tools could be the closest opportunity that physician has for a second opinion before they make a decision on the course of treatment. We can also imagine non-experts being able to triage cases for a physician to see, right? So things like pneumonia or pneumothorax are things that should immediately be brought to the attention of a physician. And maybe there's 200 cases to get through in the morning, and 6 of them have really life-threatening results that they should be able to see in those. So they should be looked at first, right? So we can aid in this, as well as identifying rare diseases. This is something we're still working on, but this is a kind of a nice direction that this tool could do. It could go. Great. All right. So Jan Kuhn said this project was nice, so I include a quote here. Okay, so there's a few reasons why we need to kind of put a chest X-ray tool in a browser. Okay, so we could ship a desktop application. That would take money. We don't have any money. We're a university. Well, we don't have any money for this. So we need to be able to do this in a way that it's free, right? And we also can't pay for the computation of processing all these X-rays, right? So if we made some free web-based tool, we couldn't have a serving server that actually does the processing in a sustainable way forever that's not reliant on donations. So in this way, we just want to offload the cost to the user's device. And to have them install software themselves from GitHub is probably not something a physician is going to do. So instead, we can deliver all the code in a web browser, right? So there's absolutely no setup, right? It can run on any device that has a web browser. Essentially, definitely anything Chrome runs on, also works in Firefox and Safari. But we're able to deliver this in a very elegant way, right? Without any setup. And there's some other issues that are interesting to talk about in this case where we also have to give away this tool for free, because when we start charging money, we go into this regulatory space, right? Which is kind of the reason we do this project in the first place, that physicians and radiologists are scared of these tools because companies say, oh, they work really well. AI is like really able to read these tools when the performance is not 100%, right? And we should be really honest as researchers talking to physicians to make sure they really know the extent of the power of these tools, right? So they can really see how this can impact them, right? So to kind of bridge the gap and make sure people aren't afraid of these tools. So getting these things into, in front of these radiologists so they can just play with them is a challenge, and there's a lot of stuff in the way. So the best way is just give them a URL they can go to. Nothing stands in the way. There's no IT department. There's no red tape at their hospital. There's no money that needs to be paid to make this thing happen. So it really enables that use case, and there's really no other way to do it unless you got the doctor to sit down in your lab and show them on your computer, right? So it's a really game changer. So we can compute DenseNet in a browser in about 1 second once it's loaded. We also need to do auto-distribution detection. So it's an interesting challenge for the kind of expectation matching of the physician or the radiologist and a tool. So we don't want to process images of cats or regular bones. We want to make sure that only correct x-rays go through, so we maintain a certain level of accuracy. We do this with an autoencoder. Autoencoders are great, which we also run in the browser. We also need to compute gradients. So why do we have to do this? We want to show a saliency map. And to do that, we need to compute the gradients of the image pixels to the output, right? We could ship 2 models. That would be like the simplest kind of code way, right? We ship one that predicts the actual pathology and another one that just computes the gradients for the input image. But that's a lot of work, and it's kind of annoying. So what we can do instead is just perform autodiff in the browser to make the new graph, which computes the gradients, right? Which is kind of magical. And then we compute on that graph and we get the gradients. We also do that with TensorFlow.js. So okay, thank you.
Thank you, Joseph. And another example I want to show you is developed by the community is the cognitive open tech group at IBM, who gave a talk on this yesterday, is developing a parasite detection web app, which runs an image classification model in the browser, so it is easy to deploy and run offline in the field. And also the library was launched last year, and in this March, we released version 1.0. We have seen huge adoption by the community with the impressive downloads and usage numbers. And there are a lot of developers who are building add-on libraries and extensions on top of TensorFlow.js. And these are extending TensorFlow.js in a very useful way. And we have a variety of resources to help you get started. A couple I want to highlight is a book called Deep Learning with JavaScript, which is written by our colleague in TensorFlow team. It provides a variety of machine learning examples written with TensorFlow.js. And there are some courses available online. We have an official website hosting the guides, demos, tutorials, and our API documentations. The website also lists all the pre-trained models we provide. Our code is totally open source, and you can find them in our GitHub repo. And if you have any questions or idea, you can email us at tensorflowjs@google.com or join our Google group tfjs@tensorflow.org. And you can also try our demo and meet our team in the demo booth. Thank you.